Hey guys, in today's video, I'll show you how to learn AP Chemistry, and today is the first part, where we learn about the Dalton's atomic theory and the discovery of the three fundamental particles. So the first thing that led to Dalton's atomic theory was Antoine Lavoisier's law of conservation of matter. This law states that in a chemical reaction, the mass of the reactants, which are the chemicals that react, are the same as the mass of the product, which are the compounds that are produced in the reaction. For instance, in the double displacement reaction that produced calcium carbonate, which is in one of my videos, right here and in the description, if we look at each chemical, we can get 1 mole of each of them. We get 110 grams of calcium chloride, 106 grams of sodium carbonate, 100 grams of calcium carbonate, and 258 grams of sodium chloride. If we add all of them together, we get 216 grams for the reactants and 216 grams for the product, meaning that Lavoisier's experiments proved this theory true. Another thing that led to Dalton's atomic theory was the law of constant composition. For instance, in mercuric oxide, aka mercury 2 oxide, the composition of mercury and oxygen in the mercuric oxide is always the same, and 92% for mercury and 8% for oxygen always. And this led to the 3 laws of Dalton's atomic theory. The first law is that all matter, including us, everything you can see right now, is made of tiny indivisible particles known as atoms. These atoms cannot be created, destroyed, or chopped into 2 or more pieces. Next, the second rule is that each atom of an element is the same as every single other atom of the element, and it is always different from the atoms of other elements. For instance, if number 2 is correct, this hydrogen atom over here will have the same properties, like say the mass, the reactivity, the amount of bonds it can produce, the amount of electrons, and blah blah blah. Everything else is the same as the other hydrogen atom here. This all was soon disputed by the fact that isotopes exist, but Dalton's atomic theory is still a very important topic in chemistry. And finally, third, reactions, specifically chemical reactions, are just simple swapping of atoms from one combination to another. For instance, in the reaction of silver nitrate with sodium chloride, we can get silver chloride and sodium nitrate. You can see that the atoms just swap places, and they didn't get new atoms or get rid of any. Now keep in mind that any scientific theory can lead to new predictions. Experiments can be used to either support a theory or disprove it. Keep in mind though that you can't use an experiment to prove that a theory is true, but you can use it to support the theory. So, a few years later after his atomic theory, where Dalton had created between 1803 and 1808, he made the law of multiple proportions. This means that if 2 elements, in our case nitrogen and oxygen, are combined to make many different compounds, and I take samples of each of these compounds so that each of the compounds have the same mass of one element, then the ratio of one element to the other will be in whole number ratios. Let's look at it. So here I listed 5 nitrogen oxides: nitrous oxide, nitric oxide, dinitrogen trioxide, nitrogen dioxide, and dinitrogen pentoxide. If we look at the mass of each of the elements, that is in whole numbers, we get 28 to 16, 14 to 16, 28 to 48, 14 to 32, 28 to 80 for each of these. If we simplify these ratios, we get 7 to 4, 7 to 8, and so on. So, this just goes to show that his theory of multiple proportions was indeed true. Now let's look at the other discoveries. In 1834, our famous Michael Faraday had discovered a very important topic that is still important in the 21st century. And it is the fact that electric current can cause chemical reactions. Some of the main uses that this is used today is in gold plating rings. I know, I don't think you had an idea that it was behind all this, but electroplating is an important topic in jewelry as well. So here, there are two poles of a battery, the cathode and the anode. The cathode is a negative pole and the anode is a positive pole. Here, the gold 3 plus ions in our example is getting reduced at the cathode to elemental gold, while this electrode is being dissolved into solution because the anode is taking away its electrons. Or, in another example, maybe there are oxidizable anions like chloride or bromide where the electrode can take. In the 1870s, Sir William Crookes had developed something known as a cathode ray tube. Now, William Crookes, even though these cathode rays are electrons, he mistakenly thought it was negatively charged molecules. Of course, here, back about 12 years, a while later, J.J. Thomson will correct the mistake. But back to William Crookes. Sir William Crookes was actually the first person to suggest the existence of isotopes. I think I made a video about this a while ago, but just in case you didn't see it, an isotope is just two atoms of the same element, in our case carbon, which has the same number of protons but different amount of neutrons, giving it a different mass. Carbon has three prominent isotopes: carbon 12, which is the most prominent, carbon 13, and carbon 14, which is used for carbon dating. Okay, so J.J. Thomson used an experiment to discover the electron. So first, of course, he needed the cathode ray tube. Here's a negative pole, the cathode, and here goes the anode. The anode had the job of narrowing down the cathode rays, and also, we also need a positive pole for the charged electricity anyway. Then the electrons are going to the sensor here. Now, when there was these two charged plates, the electron wanted to go toward the positive pole, right? Because electrons are negatively charged. So they obviously have an affinity for the positive charged ones, right? Opposite sides repel. And same sides repel, opposites attract. Same for a magnet. Anyway, another thing J.J. Thomson had discovered, not only the electron, was also its charge per mass ratio. He said that 1 mole of electron, 1 gram of electron, contains negative 1.76 times 10 to the 8th power coulombs. This is a lot of power. 15 coulombs is the charge of a lightning bolt. So you can imagine that this is an extremely big amount of charge. About a while later, Robert Millikan, another scientist, had found that 1 electron has a charge of negative 1.6 times 10 to the negative 19 coulombs. So, if we just do some simple math, we can see that the Coulomb unit cancels, and we get approximately 9.11 times 10 to the negative 28 power grams. This is a very small number, and because of this, when you're writing a more massive a substance, you usually don't count the electron. Also, this equation helped Thomson develop something called the plumping model, which looks something like this. That electrons are inside a sea of positive charges along with it, and also, if you don't know what a plumping looks like, you can kind of imagine it like a chocolate chip cookie. They look pretty similar. Later, Ernest Rutherford, along with two others, had done the so-called gold foil experiment. The gold foil experiment was where an alpha particle source was shot. The alpha particles are shot into some thin gold foil. Almost all of the alpha particles just went straight through it, but a few of them had managed to go reflect in weird directions. However, if the plumping theory was correct, this wouldn't be possible. This is because the positively charged alpha particles will be repelled by the positively charged particles inside the atom, but get attracted by the electrons. So therefore, if the plumping model was correct, the alpha particles would have just gone straight through or got bent a little bit. However, some had managed to go all the way across, like reflected to the other side of the gold foil. So, Rutherford made the nuclear model of the atom. The nuclear model of the atom states that there's a large atom and a tiny central nucleus where all the positive charge is concentrated inside it. So, the alpha particle that got too close to the nucleus will get launched away from it, but the alpha particles will just go through the electrons. A fun fact is that if the atom was the size of a baseball field, let me draw it here. Home plate. So if the atom was the size of a baseball field, like this, then the core or the nucleus would be the size of a few centimeters. I know, it's insanely tiny. And later, Rutherford also did another great discovery of discovering the proton, the second of the fundamental particles. He found that the mass in grams was 1.67 times 10 to the negative 24th, and the mass was 1,836 times heavier than that of an electron. Also, a few years later, James Chadwick also finds the neutron, the third of the three fundamental particles. Unlike the proton and the electron, which are both charged, the neutron bears no charge, which kind of explains the name neutron, which derives from neutral. Also, the mass is very similar to the proton. How he discovered it was that an alpha particle source, such as polonium, was used to launch alpha particles at a sheet of beryllium. Without the paraffin layer, nothing was detected in the sensor, but when you added the paraffin, something made the sensor detect something, and that was the neutron as well. When the beryllium was reacting with the alpha particles, it produced carbon-13. This carbon-13, however, will much prefer becoming carbon-12, and in that case it released a neutron. The neutron then collided with the paraffin molecules, which is somewhat similar to candle wax, had released protons, and by releasing, the neutrons came in and knocked off the protons for the center to detect. Here in this chart, I got some data about the three fundamental particles. The electron, or as simple as E or E minus, the charge in coulombs is negative 1.6 times 10 to the negative 19, where the relative charge is only negative 1. The mass in terms of grams was 9.1 times 10 to the negative 28, which in the terms of relative mass is 0.00054886. And because it's so tiny, we don't really notice the electron when we're writing the molar mass of a substance. The proton symbol is P or P plus, and its charge is 1.6 times 10 to the 19, negative 19 coulombs, and the relative charge is just plus 1. As you can see, the electron's charge is similar to the proton's charge, except it's either negative or positive. The mass in terms of grams is very high, at 1.673 times 10 to the negative 24, or relative mass is 1.0073. The neutron is very similar to the proton's mass, at 1.675 times 10 to the negative 24, or in terms of relative mass, 1.0087. Like I said before, though, the charge is 0. So, in today's video, we learned about Dalton's atomic theory and the three fundamental particles. Thanks for watching, and see you in our next AP Chemistry videos. Bye!